So the idea of statistical mechanics is that, as you have seen, you can describe the macroscopic properties of matter with thermodynamics. Okay, and thermodynamics is based on is an empirical science. Okay, it's based on experiments. What is this? Okay, so I should. Okay, so. So the origin of thermodynamics is from experiments. And essentially what thermodynamics tells you is that there are laws, the first and the second law of thermodynamics. If you want also the zeroth law and the third law. But there are essentially laws which are conservation of energy and the second law of thermodynamics, which essentially allow you to discuss and to discuss the properties of matter. And they are based, and they organize essentially what one measures in experiments, right? So the other thing is that in thermodynamics, one sees not only concepts or quantities which are related to the physical properties of systems, such as pressure, magnetic field, or volume, etc., etc. But also see that there are some concepts which arise, such as heat, temperature, and entropy. And these quantities do not have any analog in classical mechanics. Okay, so you cannot talk about the temperature of a particle. You can talk about the momentum, you can talk about the position, the energy. Also, the entropy is a concept which arises from studying thermodynamic transformation, but it really has no analog in classical mechanics or in quantum mechanics. Okay. So the idea is that one would like to derive the laws of thermodynamics from the laws of mechanics, either classical or quantum. And this is essentially what we are going to do. And the important realization, which we are going to see very soon, is that when many of the laws of thermodynamics do not have an origin in the mechanics, in classical mechanics or in quantum mechanics, but they have a statistical origin. Okay, so this is why, in order to explain thermodynamics, one has to combine statistics and mechanics. Okay. This not only will allow us to understand and derive the laws of thermodynamics, but it also will allow us to understand what is the nature of these quantities here. Okay, and how these quantities here are not so much related to mechanical properties, but they are related to statistical properties. Okay, so okay, so this is a very general introduction. So what we will do in this course is mostly to focus on equilibrium systems. So how are equilibrium systems defined? Well, empirically, they are defined, a system is in equilibrium if there is no measurable dynamics going on in the system. Okay? And also, since we are discussing, I mean, for example, there will not be moving parts. And also the other thing is that the system will be homogeneous. By this, what I mean is that if you measure intensive quantities, they will take the same value in all the parts of the system. Okay, you know that in describing the thermodynamics, you have extensive quantities and intensive quantities. Okay, right? So these are quantities which are proportional to the volume of the system, the number of particles of the system. These are properties which do not depend on the volume of the system. Okay, and so an homogeneous system is one. So this is, for example, the number of particles, the volume, the energy. This is, for example, the temperature, the pressure, the magnetic polarization, etc., etc. Okay. So in an homogeneous system, the temperature, for example, measured in all the parts of the system will be the same. And the pressure in all the parts of the system will be the same. Okay? And what we will do is, typically we study systems where the number of particles is very, very large. And it's typically of the order of the Avogadro's number, which is 2 to the 23. Okay, so this is an astronomically large number. And so what it makes sense to do from a theoretical point of view is to study what is called the thermodynamic limit. The thermodynamic limit is the limit where the number of particles goes to infinity, the volume also goes to infinity, all extensive quantities go to infinity, but with a fixed ratio. So, for example, we require that the density, the number of particles per unit volume, be finite. Likewise, the energy density, or if you want the energy per particle, will be finite. Okay. Yeah, please.
What do you mean? We don't have measurable dynamics going on at equilibrium. What does it mean?
No, I mean, so at the level of these quantities, you cannot observe these quantities. You cannot observe any dynamics. Okay. Of course, the system is composed of particles, is composed of atoms, and they will undergo a certain dynamics. But in equilibrium, this dynamic will be such that these quantities do not change in time. Okay? Okay, so So the system we are going to study, so our systems, we are going to study a generic system where the number of particles with n particles in a volume V and with energy E. So we think of our system as being an isolated system in a volume, okay? And there are particles inside. I'm not specifying what type of particles I'm discussing. And the energy, well, the simplest type of systems are those where the particles are non-interacting. So for a non-interacting system, you can think that the energy will be the sum over all the particles of the energy of the particles. Okay, so this is a sum R runs over from 1 to n. And this is the energy of particle number R. Okay. The other ways in which you can write this is to say that if you have quantum particles, they will be in energy levels. Okay. So you can write this as a sum over the levels of the system, the number of particles in each level times the energy, let me call it EL, the eigenstate of the Lth energy level. Okay? And of course, so this number n of L will satisfy the condition that this must be equal to n. Okay? So, of course, there is no non-interacting system in nature. So this is a very idealized system, but in many physical, for many physical systems, this is a good approximation of physical systems, and also it provides a lot of intuition for the for how to relate thermodynamics to statistical to mechanics. Okay, so we are going to deal mostly with non-interacting systems in this course. And maybe at the end we will discuss how you go about in discussing the effects of interactions. Okay? Yep.
Here, in the thermodynamic limit, we say that the number of particles is comparable to Avogadro's number, right?
Yep.
Now, do we have something for some scale for the volume?
Well, the volume is macroscopic. Okay, so it's of the order of meters. Okay, of the order of centimeters. Okay, so it's a macroscopic object. Okay, it's not of the order of angstroms, like these are the scales, of the atomic scales. Okay. Okay, so and of course we are going to discuss both classical systems and quantum systems. So in classical systems, the energy of the particles is given by the Hamiltonian, and is related. So this energy will be related to the momenta of the particle and the position of the particle by the Hamiltonian. Okay. particles will be described by a certain Hamiltonian, and this will give the Okay, so the important the fundamental idea in thermodynamics in statistical physics is that so you can define we are interested in understanding the properties of the system in terms of these variables, okay? And these variables we will call a macro state. So the specification of each of these three variables we will define a macro state of the system. Okay, and but the system itself will be defined in terms of microscopic variables. So in terms of the positions and the momenta of the particles in quantum mechanics, or in terms of the wave function of single particles in quantum mechanics, right? Okay, so so all of statistical mechanics is how you relate the macro state, which is defined by these three variables, to the micro state, which is defined by the collection of all the momenta and positions, and or by the wave functions of x. Okay, classical mechanics or in quantum mechanics. Okay, so statistical mechanics is how you derive the properties of the macro state from the micro state. And it is clear that there are many microstates which will correspond to the same macro state. Okay, you can think of a system like a gas, for example, and if you measure these quantities or quantities which you can derive from thermodynamics, you will find no appreciable deviation. So the system will be, if it is in equilibrium, it will be in one macro state. Okay, but at the microscopic level, the system will change many states, many microstates. Okay, so there are many microstates which corresponds to the same macro state. Okay, and we will call and the number of microstate which corresponds to a macro state will be which will be called omega. It's the number of microstate which corresponds to the macro state specified by these three variables. This will be a central quantity. Okay? And actually what I want to do today is to show that essentially if you compute if you are able to compute this number, then you can derive all of thermodynamics. All of thermodynamics arises from this number here. Okay, so in other words, the problem of statistical mechanics is that of computing this number. Okay, this sounds a bit magical, but actually you will convince yourself that there are good reasons why this is so. And also, in this this fact also will give us an interpretation of statistical quantities such as the entropy or temperature, etc. Okay, so just to anticipate one fact, I mean this. The number of particles is very, very large. Okay, we have already said. This number here will be even much, much larger than this. Okay, and typically it will be exponentially large in n. Okay, so this number, as we will see, is so the number of microstate which correspond to a macrostate, it's really an astronomical number, not even astronomical, it's much bigger than astronomical, okay? Because it's exponential of 10 to the 23 is really and there is a K assumption. So the K assumption is that, so when we look at a macrostate, a system which is in a particular macrostate, which particular, since there are many microstates which are which correspond to this macrostate, in which of these we will find our system, okay? Or what is the probability to find that the system will be in any particular microstate corresponding to a macrostate? So there is a K assumption in statistical mechanics that every microstate is equiprobable. A priori, microstate is equiprobable. Now this is a statement which cannot be really tested experimentally. But it can be justified in different ways, and we are going to see one from classical mechanics, which will have to do with the Liouville theorem. But the way you can think about this is that when we observe this microstate, a macrostate, the system will move from one microstate to another. And essentially, all the microstates will be visited the same number of times, okay, with the same frequency. Okay, so this is a dynamical way of justifying this thing, and this is the content of Liouville theorem, which we are going to see. Another way to justify this thing is to say, well, if there were one particular microstate which is more probable than the others, then there should be a way to, an experimental way, there should be some consequences of this. There should be some consequences, in particular there should be some experiments which is able to spot this difference, okay? But since there is no experiments which contradict this fact, or which show that some microstate has a particular relevance for a particular macrostate, or is more probable than the others, then this is the best type of assumption we can make. Okay, so this justifies this assumption. Okay. So in other words, this assumption essentially relates to what type of information we have on the system. And we have no information to distinguish between one microstate and another microstate. Okay? No one is more probable than the other a priori. Okay? Okay, so as I told you, all of statistical mechanics is about computing this object. And so what I want to do now is to show you that if you know this object, let's first assume that we know this function of these three variables. And let us derive thermodynamics from this. Okay?
This question, what does it call?
Sorry?
What does it call?
This is the number of microstates. This object, omega. You refer to the letter?
No, I saw it has a name.
It is the name is I mean is the number of microstates which correspond to a particular macrostate. It will be related to things which have an object, which have a name. So you just have to be a bit patient. Okay. Yes. Yeah.
Is that the volume of the microstate?
The volume refers to the macrostate. And so in the microstate, the microstate is the volume will enter through the constraints, which so for example the positions of a classical particles will be enclosed in a particular volume. Okay. And also the energy levels, when you compute the energy levels of a particle in a box, this will depend on the volume. Okay? I'm going to record. So the volume will enter in the properties of the single, in the problem of the single particle. Okay? And but yeah, okay. Any questions? Is everything clear? Okay, so so now, so as I told you, let's first imagine that we have a system. It's a generic system of n particles in a volume V with energy E. And imagine that omega of n P and E is known. Okay? Of course, here we are discussing an isolated system. Okay? We are discussing a system which is isolated so that the energy is constant. Okay? Now, in order to relate this number to thermodynamics, what we will do is to consider some thermodynamic transformation. Okay? So what we do is to take two systems, actually. A system A1 and a system A2. Yep.
I have a question on the key assumptions.
Yep.
Okay, let's take two systems. Okay, I mean, we have a system, and then, okay, now let's put, for instance, magnetic field. Now, okay, the particles may prefer one state because of the magnetic field.
Yeah.
And then, now let's, our system B, okay. The one
No, but if you put a magnetic field, then that will not be an isolated system,
I'm
right?
going to, okay, now I have the box and the magnetic field, and the whole system is my
So the magnetic moment is a conserved quantity, right?
okay, yeah.
Okay, so now if you put a magnetic field, then the magnetization of the system will change. Okay. Now you can study either a system which is, let's say, in equilibrium at a certain magnetic field, or a system with a fixed magnetization, right? Okay. Now, and these are two descriptions which are related but a bit different, and we are going to see this. Okay, but if you look, in the case of a magnetic system, you can think of the system as being specified by the number of particles, the energy, and maybe the total magnetization. Okay, and then this number will be all the states of the individual spins of the individual magnetic moments, which have that number of with those number of particles, with that magnetization, and with that energy. Okay. Okay. So if you so as you have seen in thermodynamics, you can describe things either with respect to these variables or with respect to conjugate variables. Okay, and this is the description which is adequate for isolated systems. So systems on which you don't which are not subject to an external force. Okay, or to okay.
So the variables can be more than, I mean, it can be anything, right? The number of variables that we put there. Omega of A, now we have 3. Number of particles, volume, energy.
Yes, this is typically for say yes, for a non-magnetic system of particles like a gas. Okay, we can think about we are studying a gas. Okay, but say for example, if you discuss yes, if you discuss a magnetic system, then you will have another variable here with the total magnetic moment. Okay, or if you discuss a moving system, then there will be the total momentum, or a rotating system, there will be the total angular momentum. Okay.
So we take microscopic variables which are constant or something?
Yeah.
Do we have some, for instance, I see some, we have certain microscopic variables which are constant,
Yeah.
and some other microscopic variables which vary with time.
Then that system is not in equilibrium. Okay.
I see that.
Okay. So we are discussing. So yes, the macroscopic state of the system can involve other variables than this. Okay. So and you can add as you said, even if you have an electric field, you have a polarization of, but here I'm taking the simplest example, just to illustrate, and then. Okay, so now imagine that we have two systems. Are there other questions? Okay, so imagine that we have two systems, and initially let's assume that they are isolated, okay? And these will have a certain number of particles, and one, a volume V1 and an energy E1. And this will have a number of particles N2, a volume V2, and an energy E2. Okay, and the number of microstate of this system will be omega 1 of N1 V1 E1, and the number of microstate here will be this. Okay. Okay, and this is omega. Sorry. Is omega 2. Now, what we can think of is the following experiment, where we replace this isolating wall between the two particles, between the two systems, with a wall which with a conducting wall, where so the two systems can exchange energy. Okay, so you can think of yes, a system which is hotter and a system which is colder, and they will start exchanging energy in the form of heat. Okay, and then as a result of this, the state of these two systems will change. Okay, and the state of the global system will change. How will it change? Okay. So the idea of how it changes is that you should look at, so you can think at all this as a system, let's call it A0. Okay. And for this system, I can write the same quantity omega, which is the total number of microstate which are consistent with a given macrostate. Okay. And of course, now these two systems are in contact, but the whole system is isolated. Okay, so the energy of the whole system is constant. The volume of the whole system is also constant. And the number of particles of the whole system is also constant. Okay, now I'm allowing these two systems to exchange energy. So E1 will change, but the sum will not change. Okay. So if I have a system, if I have this system, so how many? Imagine that I have a system where part 1 has this macrostate, and part 2 has this is in this macrostate. So then the total number of macrostate in the initial system will be equal to the product of the number of states of the two systems, right? So here I'm referring to the initial configuration where still there is no exchange of particles between the two things. Now, of course, since so this is a function of the energy of E1 because E0 is constant. So you can write this as omega 1 of E1 times omega 2 of E0 minus E1. Okay? This is E0.
Omega 0.
So this is the total number of microstate which correspond to this to a system, to an isolated system where a part of the system is in this macro state and the other part is in this other macro state. Okay? And of course, since this system can be in any of these states and this system can be in any of these states, then the total system can be in any of the states which is the product of the two. Okay? Now, however, when I put these two systems in contact and they start exchanging energy, then the energy E1 will change. Okay? And how will it change? Well, it will change in such a way that the product of these two things will be maximal. The number of macrostate of the combined system will be maximal. Okay, and so you can think. So if you look at this formula here, so you can think that this omega 0 of E1 as a function of E1. Well, when the energy of E1 will increase, the one of this other one will decrease. And the number of possible states will also decrease of the second system. Okay? Likewise, when E1 decreases, the number of states of this system will decrease and the number of states of this system will increase. So there will be generally a maximum for a certain energy E1 star. Okay? So what I'm saying is that if the two systems are in a particular energy E1 at an initial time, when you put them in contact, the system will change its state and go to and transfer part of the energy from the system 2 to the system 1 in this case. And the energy of system 1 will increase. Okay? Why is this so? Well, because you can think, if you think at the microscopic state of the combined system, so after a long time that you put these two systems in contact, so where do you expect to find the microstate? Well, the microstate of the combined system, it will be most probably found in since all the states are equiprobable, but these states are much more numerous than the other ones, then it is highly probable that I will find the system in this state here. Is this clear? No. Okay, so any state is equally probable. Okay? But the number of states of the combined system with this energy of the part 1 is much more numerous than is more numerous than states with a different value of this energy, of energy E1. Okay, so it is more probable that I will find the system in this state than in other states, just because the number of states where system 1 has this energy are more than the others. Okay? And actually, I'm plotting this in this way, but as I told you, this number here is exponentially large in n. Okay, so indeed, the number of states which have an energy which is different from this one are exponentially more rare than the states with energy E1 star. Okay? And then almost surely I will find a system in energy with energy E1 star. Okay? Just because the number of states with that, the number of microstate with that energy of system 1 is much more numerous than any other energy of system E1 or system 1. Okay? So, so E1 star will be such that omega 0 of E1 is maximal. Okay? So let us compute this maximum. Okay? So what we have to do is to take the derivative of this with respect to E1. So the derivative of omega 0 with respect to E1 from this is the derivative of omega 1 with respect to E1 times omega 2. And then here I have omega 1 times the derivative of omega 2 divided by, I should have the derivative of omega 2 with respect to E2 times the derivative of E2, which is this, times E1, but this is equal to minus 1, okay? Okay? And I can rewrite this equation in a very nicer form by saying that this is omega 1 times omega 2 times the derivative of the log of omega 1 times dE1 minus the derivative of log omega 2 divided by E2. Okay? And the condition of the maximum is that this must be equal to 0. Okay, so this will give me the energy E1 star. Okay. So by this you see that there is a quantity in when these two systems are in equilibrium. There is a quantity which I can call beta, which is the derivative of the log of this function omega with respect to the energy. And you see this equation tells you that in equilibrium you should have that this quantity in system 1 should be equal to this quantity in system 2. Beta 1 should be equal to beta 2. Okay? And actually, if the system is not in equilibrium, if the system is initially in this state, then you will have that the change in the log of omega 0 will be what? Will be essentially the see, if you divide this by, this is omega 0, so the change in the omega 0 will be beta 1 minus beta 2 times the change in the energy of system 1. Okay? And the fact that the system is not at the maximum implies that this change, when you go to the maximum, must be positive, right? Okay, you are here, you want to go here, so you have to go up. The change must be positive, okay? So beta 1 is such a quantity that if there is a transfer of energy from system 2 to system 1, if the change in energy of system 1 is positive, then beta 1 must be larger than beta 2. Okay? So if there is a transfer of heat from energy 2 to energy from system 2 to system 1, then this beta 1 should be larger than beta 2. Does this remind you of anything?
The direction of entropy.
Sorry?
Entropy.
So when you have a transfer of heat from two systems, okay? Yep. From the energy goes from the cold to the hot. Okay, the other way around. Okay, so in thermodynamics, the second Clausius statement of the second principle of thermodynamics tells you that when you put two systems in contact, the heat will flow from the hotter body to the colder body. Okay, so this is very much similar to the second law of thermodynamics. Okay, and indeed it is exactly the second. I mean, there is a perfect correspondence. And because we know that in this the change in entropy in this transformation is equal to 1 of T1, 1 of T2 times dE1. Okay. So I mean, this comes from thermodynamics, from the equilibrium. I think you have done this with Antonello Scardicchio, right? Okay, so what you can see is that the ratio between this change and the ratio and this change must be a constant. Okay, so that and this is consistent with the fact that the log of omega for a particular system the in a certain transformation, you can actually we have seen that both these two quantities will change, and actually you can argue that this will be a constant. Okay, and this tells you that the entropy of a system with n particles is proportional to the log of this total number of states, and the proportionality constant is called the Boltzmann constant. Okay. So this is the central is a central relation, statistical mechanics. You see, it relates something which you compute from the microscopic states to something from which you can derive all of thermodynamics. Okay. And this equation is called Boltzmann equation. It's called after Boltzmann, and it actually is engraved on his tomb. But actually, it was not derived by him. But okay, so and the other identification which you can do is between this parameter here and the temperature. Okay. And so if you take this definition here, then you will have that the beta is just 1 over kT. So this parameter beta is related to the entropy. And this relation here is essentially the equivalent of the relation of this thermodynamic relation. Okay? So you see, we have derived a microscopic derivation of the entropy, and as I told you, this quantity, the entropy, does not have a mechanical origin. It has an origin which is related to statistics. It's related to the number of microstates which are consistent with a particular macrostate. Okay. From this, you see that also the entropy is a measure of the degree of uncertainty that you have on the microstate of the system. Okay, so the larger is this number, the less you know which particular microstate the system is in. Okay? So the more you are uncertain about what particular microstate corresponds to a macrostate, the larger is the entropy. In this sense, the entropy is a measure of disorder. Okay? Very good. Now, we can actually take our system and start playing more with it. Now, for example, we can assume that this boundary between the two systems does not only allow energy to transfer of heat, but can also move. Okay, it's free to move between the two systems. You can think of, say, a piston being here. You can think also of this as being a flexible wall. Okay? Why will it move? Huh? Huh?
Okay, there should be some force on the wall
Yes.
which is characterized by the pressure.
Yes, exactly. Okay. So it will move if the pressure in this system is different from the pressure in this other system. Okay.
Pressure gradient, yeah.
Exactly. Okay. So we know that when we allow for this wall to move, then we are going to study transformation where pressure is involved. Okay. And we can do, you can do the same argument. Now we are keeping the number of particles fixed. Okay, so the wall will not allow particles to move. So the number of states of the system where, of the global system where this part has volume V1 will again be equal to this. So V0 minus V1. And you can do exactly the same derivation as before, but with the volume instead of the energy. And again, you can argue that, well, the system, if it is allowed to move this wall, the microstate will change, and it is highly probable that it will go, that you will find the system in a state which corresponds to a volume V1 which maximizes this quantity. Okay? So the condition is that the d omega 0 dV1, which is omega, you can write it as omega 0 times d log omega 1 dV1 minus d log omega 2 dV2 is equal to 0. So these derivatives are taken at N1 and E1 constant, and at N2 E2 constant. Okay? Now you see that the condition for equilibrium is that these two derivatives should be equal. Yep? Now the particles are not free to move yet. I will let them move in 2 minutes. Okay? Just be patient. Then maybe if you have questions, you'll ask later. Okay? So now we are not allowing particles to move from one part of to the other. We are only allowing this wall to move. Okay? And we are saying that it will move, and in equilibrium we will have a particular quantities which is d log of omega, so dV, which I can call, say, for example, eta. And in equilibrium, this tells me that eta 1 will be equal to eta 2. Now, if you do the same identification, I mean the same argument as before, and you ask yourself, well, of course, if the pressure here is larger than the pressure here, then the volume here will increase and the volume here will shrink. Okay? So by doing this, you can argue that this should be related to minus the pressure. Okay? And now you can do the other experiment, that is to say, also to allow the system to exchange after they have equilibrated the energy and the volume have equilibrated. Then you can allow the number of particles, the wall also to, you can essentially remove the wall and let particles flow from one part to the other. And then again, you will see that this quantity will be maximal. And since the total number of particles is conserved, this will mean that there is another quantity, which is the log of dn at volume and energy that I can call Z. And the equilibrium will be when Z in system 1 is equal to Z in system 2. The derivative of the log of this thing with respect to N2 is equal to the derivative of the log of this thing with respect to this one. Okay? So from these equations, you can argue. So yes, you particles are of the same kind. Yes, yes. No, that's very important because yeah. You had a question? Is it clear?
I thought we allowed the particles to move up, so I was asking why the derivative is respect to V1.
Can you speak up?
I was wondering if why the derivative is only respect to V1.
Ah, yes, yes. Because we were keeping n fixed. Okay, now we are allowing n also to change. Okay, and so if you combine these three things, you see that the differential of the change in the log of omega is related to these three parameters, which I call beta times the change in the energy, plus this eta times the change in the volume, plus this zeta times the change in the number of particles. And now you can, I mean, and this is very similar to the first law of thermodynamics, okay, which tells you that the change in energy, or the differential of the energy is Tds minus Pdv plus mu dn, okay, where this is a chemical potential. Okay, so if you relate these two equations, you can write, and you use that S is K times the log of omega. Then you can see that, well, beta, as we said, is 1 over K times T. This parameter eta is minus P divided by KT. And the parameter mu is equal to minus, so the parameter psi, or zeta, sorry, is minus mu divided by KT. Okay? So, so with respect to any transformation which you can do on a system, the log of omega behaves precisely as the entropy, okay, apart from a multiplicative factor, which is the Boltzmann constant. Okay. So Now, essentially, since do you have questions? Is everything clear? Okay. Now, notice that actually we could have put a constant here, okay? In the sense that, of course, this relation will be true even if there is a constant here, okay? So this constant is set equal to 0. And this means that when a system, when a macroscopic system corresponds to just one microscopic system, then the entropy is 0. So when omega is equal to 1, then the entropy is 0. When is the entropy 0? Huh? Do you remember anything? Third law of thermodynamics? 0 temperature, okay? So at 0 temperature, what happens at 0 temperature in a system? So so at 0 temperature, what happens is that
Everything freezes.
everything freezes. It's very cold.
I mean, kinetic energy, we don't have kinetic energy, we don't have motion.
Exactly. So the system goes to a state of minimal energy. Okay. So, and if the state if you have an energy function of your system, then there will be, I mean, if there is only one state which minimizes the energy, then it is clear that that macro state, where the energy is minimal, will correspond to just one micro state. Okay? And this is consistent with this relation here. Okay? So this is the third law of thermodynamics. Okay? Okay, so now we have a very nice recipe to compute thermodynamics, which is just, we have to compute omega of n, v, and e, or what other macroscopic variable defines my system. And this is essentially statistical mechanics. Statistical mechanics is how you compute this number. Okay? So what we will do now is to do a specific example. Okay? To compute this number for a particular case, which is the ideal gas, ideal monoatomic classical gas. Okay, what does ideal mean? Ideal means that the particles do not interact. This means non-interacting particles. Now, let me open a parenthesis on this. So we have, when we have analyzed these two systems, we have said that the energy of the total system was the energy was the sum of the two energies. of the individual systems. Okay, so we have done an approximation there because we have neglected the interaction energy between the two systems. Okay, where does the interaction come from? It comes from the fact that there is a particle here and there is a particle here, and maybe there is a potential energy between the two particles. Okay. Now, it is okay to neglect this interaction because this only occurs between particles which are close to the wall. And these are very few particles. Okay, so there are very small number of particles. It's a number which is proportional to the surface of the wall, whereas the total energy is proportional to the volumes of the two systems. Okay. So, but still, this interaction is very important. The interaction is very important because otherwise you cannot. How can you transmit energy from one system to the other? There is no way to. So the interaction should be there in order for the system to equilibrate, to transfer energy from one side to the other, but does not really matter for the calculation, okay, that we have done, okay? Okay, so in other words, the derivation which we have done is valid even for the case where these particles are interacting particles, because the interaction energy is negligible with respect to the total sum. Okay. Now, when we discuss a monoatomic classical gas of non-interacting particles, actually we have the same problem, no? Because if the particles do not interact, then how is the state going to change? How are they going to exchange energy between one particle and the other? And so how is the state going to change? If it is not in equilibrium, how is it going to go in equilibrium? So the idea is that the whole interaction which takes place in this system is that particles collide elastically one with the other. So they exchange energy and momentum, but the energy is conserved and the momentum is conserved. So there is no other interaction than this. Okay. So this means that if you want, the Hamiltonian of the system in terms of the momenta of the particles and the positions of the particles is just the kinetic energy. Okay? So there is no interaction between the particles. In particular, the Hamiltonian does not depend on the positions. Okay? So this is the sum of the energies of the individual particles. Okay? Okay, so we want to compute these numbers. So, but first, we can what we can do. So, so the system we are studying is we have a box of volume V, and there are many particles inside, many atoms, and each of them is moving around. And yes, all they are doing is hitting the walls of the box and maybe hitting one another and elastically and with this Hamiltonian. Now, one thing I can argue is that, so imagine that now I divide this system in many, many small volumes. Okay. So, imagine that I take my volume V and I split it in this number of cells, okay, where V is a small volume. And I want to argue how many ways, so how this number will depend on the volume. Okay, so for each of these particles, in how many ways can I distribute my particles in these cells? Okay, so if my particles are distinguishable, which means that I can put a label on each of them, and then I can compute this number of ways to distribute these particles in this cell by taking the first particle, and this will be in any of this cell, so I can distribute it in V divided by small v number of ways. The second particle, I can distribute it in the same number of ways. The third particle, etc., etc. So this tells me that my omega will be proportional to V divided by V to the power n. Okay? Because each particle can be distributed equally likely, I mean, in notice that another thing, I mean, the fact that the particles are non-interacting means that where particle 1 is independent of where particle 2 is. Okay, so knowing in which cell is particle 10 does not tell me anything on where particle 1 will be. Okay, so interaction, translates into independence. Okay. Now this is quite interesting because it already tells me that if I take the log of omega, the derivative of the log of omega with respect to the volume at constant n and at constant energy, then this I told you is equal to pressure divided by kT. This will be equal to n divided by V. Because the log of omega will be equal to n times the log of V plus a constant, which does not depend on V. So when I take the derivative of the log of omega with respect to V, I will just get the derivative of n times log V divided by V, which is n divided by V. Okay? So this is nice because it gives me an equation which is very familiar, which is PV is equal n kT. this is the ideal gas law. The law of ideal gas. And so you see, computing this number gives, I mean, this simple argument already gives me an interesting result. And also it allows me to relate this constant k to something which is measurable, okay, which is the ideal gas, the constant of, the universal constant of gases. So this n, you can write it as Avogadro number times number of moles. And so if you compare this with the ideal gas law, which is written as nRT, where R is the universal gas constant, this gives you that K times the Avogadro number is equal to R. Okay, and this R is what you measure experimentally, and then from this you can measure, and Avogadro's number also is measured experimentally. So from this you can get the number of Planck's constant, of Boltzmann constant, K. Okay, so I think this is probably a good point to stop, and we will continue this calculation next time and compute this number for the ideal gas. Okay? So see you on Wednesday. Yeah? Can you speak up? So,
for some systems, the entropy does not go to zero.
yes, that's true. Because particularly this happens for systems which are very, very, very disordered, okay, or which have a very degenerate ground state, where the ground state can, there are many states of low energy which take the same value, and for which the energy takes the same value. So, but if you think of, say, for example, in many solid state physics, I mean, if you have a crystalline solid, then at zero temperature it will have only one state. And, well, okay. We are,
How do we see it from the set?
so, sorry?
How do we see it from the set law of dynamics? How does it?
No, let's say, I mean, if you want, the third law of the thermodynamics is not experimentally verifiable thing, because what you can measure are changes of entropy. Okay, you cannot measure the entropy directly. So you can see the third law of the thermodynamics as a definition of the zeroth of the entropy. Okay, and from if you interpret the entropy as the log of this number, then so this tells you that when there is only one state, one microstate which corresponds to the macro state, then the entropy is zero. So this gives you a sense for this definition. Okay, but okay.